Okay, I will speak about explanation techniques, in particular in automatic machine learning environments. And let's start with some technical motivation. So we all know that in practice, data science problems are often quite messy. So for example, features that may look perfectly on train may not hold on production due to lack of stationarity. The training sets may be biased in various ways that we're not aware to, and so on. And if you think about it, in such circumstances, machine learning may not work at all. We actually don't have any guarantee, and still, of course, we would like to use it because it's such a valuable tool. So this is one line of motivation. Another major line of motivation for explanations is the fact that often, actually more often than not, I would think, we do machine learning, we do data science, but our goal is to take action, not just to make prediction. For example, we would like to prevent sickness, not just predict it. So the techniques that I'm going to discuss today, called explanation techniques, aim to make machine learning solutions much more transparent. And this transparency is going to help us to debug machine learning, so to speak, to develop models which are more robust in practice, in production. In addition, in many projects, such techniques will provide highly valuable insights. And finally, they will help us a lot in making predictions actionable. For example, if I know that an equipment not just is going to fail, but it is going to fail because it is getting too hot, I can deal with the problem much more efficiently. I can actually prevent it much more efficiently. Okay, so this is the topic of today's talk. Now, when we speak about explanations, or when we speak about transparency of machine learning systems, I would like to focus on two major or two fundamental levels of machine learning systems. The first one is the feature level, and the second one is the classifier level. On the feature level, the goal is to communicate the hypothesis used by the classifier to domain experts, to the users. And the idea is that domain experts or users will then be able to exploit their human intelligence and word knowledge or word understanding in order to verify that these hypotheses, these features, would indeed hold in production. By the way, there's, at least to my knowledge, there are only very little research on this topic. On the second level, which is the classifier level, there is a nice emerging literature, and this is about explaining the classifier's prediction given the features. So here we can speak about two major subtopics. We can speak about explaining specific examples or sets of examples, and this is going to be the focus of this talk. And we can also speak about explaining the classifier as a whole, and I will not touch this issue much in this topic, in this talk. Now, before I dive into the feature level, let me tell you a few words about Spark Beyond, about our technology, because it's going to be relevant for the rest of the talk. We developed a general-purpose automated research engine that in particular is capable of taking data and very rapidly turn it into features, models, and insights, like really, really rapidly. And in fact, this engine is going to go over a very large hypothesis space, which is also include exploiting many forms of external knowledge. So this is something that will take a data scientist a very long time to obtain. And it's a paradigm shift. So data scientists can work in many rapid iterations, focusing on much deeper thinking and technical aspects of feature and feature engineering and model construction to the machine. Also, it supports retraining and things that people talked about today in a few talks. Now, from now on, all the examples that I'm going to give are going to be very closely based on the output of the engine. Okay? So the next thing I would like to do is to focus on the feature level, and I want to show you a few features. I want to discuss a few features automatically discovered by our engine in various projects, and I would like to show you how do we communicate them to the user and why this is so important to do. So here's the first feature, and it says that shops of a certain type, if they are located near a recreational park, they are going to be more successful. Now, this is something, I mean, when I put such a statement like that, this is something that a domain expert can review, okay? And in this case, it turned out to be a true phenomenon. And note that this is, firstly, it's insightful, but it's also highly actionable, right? If I write a statement like this, the customer can immediately improve its business value, okay? It can act upon this, such a feature, such a finding. Now, about communicating the feature, let me comment that originally, this feature was an auto-generated code involving just the shop's location and some external research that was looked up automatically. And we invest a lot in a process that we call humanization that automatically turns such a code into human-readable statements such as the above. There are many interesting challenges around that. We also invest a lot in visualization, in giving meaningful examples, and so on. So users can really explore the features that the engine discovers. Here is a more intuitive feature from a different project. It says that if colorful gadgets tend to be cheaper. Now, and again, it was found by text analysis. It's not a direct, something which is direct on the data set. And it looks a bit surprising on a first glance, but once you see a few examples, it's become clear that the population that such gadgets are meant for is of a certain kind. On the other hand, let's see another feature from a different project. And in this project, we have to classify or flag out sites which contain a certain content that I don't want to mention. Okay? And one of the features that popped up said that sites written in the Polish language are more likely to contain this content. And as a human, this doesn't make a lot of sense. I mean, from the data science, I mean, that's just from a statistical perspective, the feature was true. But it doesn't make a lot of sense, right? Why is that? And indeed, it turned out that this feature is actually a false discovery, and it is related to an ill data collection process of the customer. Okay, and this is something which is not in the data. We could only discover that because we translate it into a human-readable form, and this contradicted our own intuition. So the message that I would like to convey here is that machines still have little ability to spot such issues, okay? And it currently takes human intelligence, word knowledge, intuition, etc., even to see that there is a problem. And let me make a bold statement and say that models that don't expose their features to the users or to domain experts might lead into poor performance in the field because the hypothesis may crash miserably in production. Okay, now I would like to switch gears and speak about the classifier level. And our setup is going to be fairly standard in the emerging literature on explaining classifier decision. We are going to assume that the feature and the classifier are given, and our goal is going to be to explain the predicted labels. Now, my own personal view here is that there are many reasons to do so. There are many usage scenarios, and different usage scenarios may require different explanation techniques, or even combination of explanation techniques. So what I'm going to do, I'm going to first present our own algorithms along with their leading usage patterns, and according to the time, I will survey some of the existing emerging literature on the topic. Let me start with usage pattern, which I personally like a lot. And this is a pattern where we would like to argue for specific predictions. And let me first give you some motivation. I mean, why would we like to do so? So the first case is high-cost decision. I often want to use machine learning models in order to come out with better decisions, and in particular, better high-cost decisions. So for example, I want to decide where to drill for oil, where to send someone to an operation, and so on. So in this case, I want to be sure on a specific decision. I cannot just trust the law of large numbers, okay? And I want to be able to allow someone to carefully review this particular decision of where to drill for oil. This is one motivation. Another motivation is what I already mentioned, is that we often want to act upon the predictions. For example, if I know not just only which customers are going to churn, but also why they're going to churn, for example, because they called the support center a few times and then they didn't get an answer, I can do a lot to prevent that. If I know why an apartment worth this and that, I could sell it better, and so on. And there are lots of other motivations for doing that as well. So here is an algorithm that we developed and are using at the company. And the goal of the algorithm is to find direct evidence from the data, justifying the prediction. The input here is a labeled training set, as well as the train and the test enriched with discretized features. Now, we can speak a lot about how to discretize. I don't want to do it today. Another input, the second input, is the test set that I would like to explain along with the predictions. So the algo, and let's just mentally think about regression. I can speak about, but the algorithm works for classification, either binary or multiclass, similarly. So there are two stages, pre-processing and the actual computation. In the pre-processing stage, I would like to take each feature J and the value V, and I'm going to map this pair into the train population, all the instances, all the rows in the train that have this value for this feature. For example, all the people which are above 180 centimeters, for instance. This is one thing that I'm going to do. The second thing is that I'm going to go over all my training set and compute the average label. Okay, this is going to be my initial estimation. And now, for each instance R that I would like to explain, I want to do the following. Let P be the current population. I initially start from all the train instances. And then I greedily go over all my features, well, the estimation is not satisfactory. I mean, while it's still far from the predicted label, and I have enough instances to work with, I'm going to do the following. I'm going to go over all my remaining features that I didn't select yet, and I'm going to denote by S of J to be all the instances, all the rows from the current population that also have this value, exactly like the example that I want to explain, the same value as this example, okay? And then from all the features, I choose the feature J, whose average on the new population is the closest to the prediction. So at each step, I take the feature that brings me closest to the prediction. It's a sketch. There are some more details, but basically that's the algorithm. It's very fast. It's just intersecting sets. And let's see the result. So this is from house pricing data set. And I would like to explain why a certain apartment is fairly pricey. It's around Boston. So it turns out that the neighborhood is Northridge. It's probably the most expensive area around Boston. There are at least 3 garage cars, and the kitchen quality, or the quality is excellent. So there are at least 30 apartments like this, and the overall price is quite high. So this is a pretty convincing explanation. It also gives me a very nice segmentation. I personally like to take a data set, look at all the explanations, and it gives me a lot of insight on the data set just by doing that. The second example is from the Titanic. If you are a female and your passenger class is not the third, then you're in a pretty good shape, much better than the average Titanic passenger. Okay, here is another algorithm. And the goal of this algorithm, the main motivation, is to do error analysis. This is something that is greatly improve the accuracy of algorithms. So what I'm going to do here, I'm going to go over specific instances, in particular instances where I made errors on, and I'm going to look at them, and I'm going to think whether I'm missing some features. I can also think whether there are features that look spooky to me, but the first pattern is the most interesting to me. And we are going to do this as follows. Again, we're going to have a pre-processing stage and a computation stage, which is very, very efficient. In the pre-processing, for each label and for each feature J and the value of this feature, we are going to compute the strength. I mean, how much this feature is telling me about the label. And just choose your favorite strength measure. I mean, it can be, we like information gain, but you can choose lift, I mean, whatever. And now the algorithm is very, very efficient. For each instance row that I would like to explain, I'm looking at the predicted label, and then for this label, I just output the strongest features of this particular instance, the strongest features that support it, and the strongest features that oppose it. That's the whole algorithm. It's very, very efficient for error analysis, or very, very effective for error analysis, and for other use cases as well. So where else explanations or transparency is important? It's, I think, crucial for anomaly detection. In anomaly detection, there are many reasons why something is an anomaly. I want to separate the irrelevant and relevant anomalies. I already mentioned help acting upon the model. It's very effective in terms of segmentation and so on. Okay. So let me say a few words on the existing literature. I won't dive deep into it. At least in my opinion, the most interesting approach for explanation is the local approach, led probably by the Lime paper from a few years ago. And here, the trick or the technique is to explain the classifier's prediction by a simple interpretable classifier that locally agrees with with the classifier on the example or around the example. Again, I'm going to say my personal thoughts now. So firstly, the idea is very cool. It's very intriguing. In fact, I'm very interested in combining the approach that I described beforehand and the local approach. I also see quite a lot of potential drawbacks to this approach. And in particular, it's a bit hard for me in many situations to assign some semantics to the locality property, and then it's a bit difficult for me to find how exactly to use such algorithms. But again, that's just my own personal taste. There are also global approaches that are, I think, they're very related to trees. And again, it's my own personal opinion. I think they're very relevant to explaining the boundary surface as a whole. They may be less relevant to specific examples. So, for example, to explain why I personally should take a medical exam, I'm not that interested in the whole decision flow of the algorithm. Okay, let me wrap up the talk. We started by speaking about motivation, about why do we need transparency, why this is so important. And our main motivations were to enable robustification and refinement of models. I would also mention monitoring, in particular in light of quite a lot of talks you've heard here today. The second motivation was to act upon predictions. So that was the motivational part. Then we spoke about the level of communicating the features, and I gave you a few examples of from the output of Spark Beyond engine on various projects. And then we spoke about explaining the classifier decisions, and I showed you two algorithms that we like to use at Spark Beyond. Actually, we use them in combination with each other. We spoke just a tiny bit about the existing literature, and I briefly touched various usage patterns. So that's it, basically. Feel free to drop me a line or visit our website.